Hello everyone. Okay, this video I'm going to finish the second part of the example 16.6. Okay, let's look at the 16.6. It say, okay, find the maximum deflection of the beam. Assume EI is a constant. Okay, and in the previous video, okay, or previous part one, we already solved the elastic curve function. Okay, and next one we have, okay, by this elastic curve function, we have to find the maximum deflection. Okay, and then we need information of the elastic curve and the first derivative of the elastic curve. Okay, for the finding for this problem, finding the maximum deflection. Okay, let's first of all let's check the boundary. Okay, in fact we have some boundary in the system. Okay, for example, we have boundary for A and B. Okay, and also we have another boundary called C. Okay, so let's check the boundary. Okay, the displacement of a boundary, I think for x equal to 3 and x equal to 9, we already know it. Okay, but let me write down let me write down the information. Okay, so we already, let's check the boundary. Okay, let's check the boundary. Check the boundary. UNDARY. Okay, and we already know nu of 3 is equal to 0, and nu of 9 is equal to 0. Okay, and let's check another boundary. What about nu equal to 0? Yeah, 0 is also a boundary, right? So, okay, what is nu 0? Okay, so just put 0 inside, put a 0 in this x. Okay, we can get a nu 0. Okay, nu 0. So okay, so we'll have EI nu 0 equal to, put replace x by 0. So this one's 0. And the second term z minus 3 is negative, so the whole function is all 0. Okay, and put the 0 in the x, this term is also 0, so we only have the minus 1395. Okay, or 1395. Okay, but it's negative. Okay, and but the EI is a constant, right? So EI is constant, so we can have we will have V na nu na, okay, minus 1395 divided by EI. Okay, this is the displacement at equals to 0. Okay, this is a deflection at x to equal to 0. Okay, so and let us okay, so between x 0 to 3, between between BETWEEN, between x, between 0 and 3. Okay, x between 0 and 3. Okay, let us draw a graph here. Okay, for example, if let's say, because we already know, let's say, okay, this one here, this x equal to 0, this is x equal to 3. Okay, and we know the displacement. Let's say, okay, it's this one is 0. Okay, is the coordinate of the system. Okay, if the here is the standard, here is 0, here is 0. Okay, and what's the deflection at x equal to 0? It's minus 1395 divided by EI. So the displacement is negative, and its value is EI and 1395. Okay, and it's negative. Okay, we said this, the 0 is here. Okay, and what's the displacement at x equal to 3? It's 0, right? Okay, so So we know the information for the displacement at x to equal to 0 and x equal to 3. And okay, for the elastic curve, we can assume the elastic curve. We can assume the elastic curve is smooth and continuous. Okay, elastic curve is, we assume the elastic curve is very smooth and continuous. That means there is no radical change between the boundary. There is no radical change between boundary. Okay, no radical, no radical change. No radical variation, radical variation between boundary, between BOU and DAR. Okay, so if the displacement at x equal to 0 is here and x equal to 3 is 0, so what the elastic curve would be? Okay, we have two boundary here. Okay, two boundary here. Okay, what the elastic curve could be? Okay, because we assume it's smooth and continuous, so maybe we can, so the elastic curve may be like this. Okay, like this, or maybe like this. Okay, okay, or okay. Okay, the elastic curve between 0 and 3 maybe like this. Okay, slow growth or increasing growth. Okay, maybe, or possible, I don't know. Okay, okay, or but no matter what, no matter what, okay, no matter what, okay, no matter what, there is no minimum or maximum. Okay, there is no minimum or maximum between at this range x equal to 0 and 3. Okay, okay, because we assume the elastic curve is smooth and continuous. So wherever perceive x is equal to 0 is negative and x equal to 3 is 0. So there's only this situation for the elastic curve, but no matter what situation, there is no maximum or minimum between this range. Okay. Okay, so for that means the maximum and minimum must be, so from this logic, okay, the maximum or minimum must be between x to 9, x between 3 and 9 must be in x between 3 and 9. Okay, so let's find out elastic curve. So we need to know the elastic curve. Okay, at x between 3 and 9. Okay. Okay, so what's the elastic curve for x equal between 3 and 9? Okay, we already have the elastic curve function. Okay, is here, right? Is here. Okay, so and we also have the first derivative of elastic curve function here. Okay, so let me can we move this? Okay, so yeah, I'm not sure. Can we? Yeah, what's wrong with this? Okay. Yeah. 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 Sorry. Oh, let me pause the video recording right now. Okay. I'll back in a minute. Sorry. Let me pause it. I have some technical issue here. Pause. Okay, hello, I'm back. Okay, I fix the technical issue. Okay. Okay, so we continue. So so the minimum for this problem, minimum or maximum of the elastic curve must be between for x between 3 and 9. Okay, so we already solved the elastic curve function and first derivative of the elastic curve function. Okay, let's put when x between 3 and 9, what the function would be. What the function would be. Okay, let me write down this. Okay, let me write down this. Okay, so for x, for x between, I think, for x, I don't think we don't have need much change, right? Okay, so first of all, so next thing we want to find a maximum or minimum of the elastic curve. So we need the first derivative equal to 0, right? First derivative equal to 0, that means you have maximum or minimum, right? Okay, and then so we put the information in there. So it will have EI, with dv over dx, but it's 0, okay? So the right now x is between 3 and 9, so we keep this function, x squared and plus and x between 3 and 9. Oh yeah, we also keep this function. Okay, that will become x minus 3 squared and plus 517.5. Okay, because we now assume that first derivative of elastic curve with respect to x is 0, so this one is 0. Okay, so what we will get a second order polynomial, second order equation. Also, okay, let me write down the equation. Yeah, but we don't have much time. Yeah, okay. We will have the equation. Let me see. We will have the 3.75 x squared plus 82.5 x minus 641.25 equal to 0. Okay. Okay, we have second order. We have second order equation. Oh, why does it disappear? Okay. Anything wrong with the? Okay, I have a second order equation here. Okay, and then, you can solve the x. Okay, what is x? X equal to 2 times 3.75 minus 82.5 plus minus square minus minus 4 times 3.75, is plus, times 64125. So using your calculator, you will find a meaningful solution for the x is equal to x, meaningful solution, meaningful solution. Because you get a two solution, but one is meaningful. The meaningful solution is x equal to 6.088. The unit is in. That means for the elastic curve between x between 3 and 9, for x equal to 6.088, there will be a minimum or maximum. So let's put x equal to 6.055 back into the elastic curve function. So what will we get? Well, what we will get. Well, let me change this color. Maybe change it to each color. So we'll have EI. V of 6.088. Put the x, replace this x by 6.088. So the first term is say minus 35 over 6, 6.088 power 3 plus 627.5. Okay, here 6.088, okay, minus 3 will be equal to 3.088. It's greater than 0, so I keep it. And its power is 1. Okay, keep it. Okay, and plus 11517.5. Okay, so 6.088. Okay, and minus 1395. Okay, so after all, what's the final answer? Okay, using your calculator. Okay, my answer here is, this will be, I think, 574.25. Okay, so the displacement at the x equal to 6.088 is equal to EI. Okay, 57425. Okay, that means what the situation what the situation looks like. It means, okay, we have this is x equal to 3. It's x equal to 3 here, and here is x equal to 9. Okay, and we know that displacement at least two boundary is all 0, 0, right? Okay, and then 6.6, where is the 6? Okay, maybe 6. Where is the 6? 9. Maybe it's around here. So displacement will be like this. Okay, because we assume the elastic curve and smooth and continuous. Okay. Yeah. Ah. Okay, maybe just put it here. Okay, here is x equal to 9. Okay, and now displacement and deflection is here. Deflection is here. Is x equal to 6.088. Okay, and the displacement is this value. Okay, and it's positive. That means position. That means the position is I think okay, the position is upward. Okay. Okay, so we have we found a maximum displacement between x from 3 to 9. Okay, but don't forget we also in previously we have the result that the displacement at 0 is, okay, EI over minus 1395. Okay, because this problem only want the maximum deformation. Okay, so the positive negative is not the issue here. The only thing matter is the magnitude. Okay, so the displacement magnitude at the displacement at the magnitude at the position 0, the magnitude at position 0 is greater than the displacement at the x equal to 6.088. Okay, so the maximum deformation is at the position 0. So the maximum displacement, okay, at x equal to 0. Okay, so that's the answer for this problem. Okay, so for finding the maximum deflection of the beam, yeah, first of all, you can check the boundary. Okay, and also you can check the first, you have to use the first derivative. Okay, because the maximum and minimum in your calculus class, if you want to find the maximum or minimum, you need the first derivative of the function is equal to 0. Okay, so you need the function first the function that is the first derivative of the elastic curve. So you have to use this information. Okay, and then if you want to calculate, okay, after you find the position, but you have to put the x back into the elastic curve to find the displacement. Okay, so this calculation yes, take a while. Okay, so I finished the problem here. Okay, hopefully this can help you to understand this problem more. Okay, see you in another video. Bye bye. Yeah, this is dead.